In this R code tutorial, we'll explore how to build and evaluate logistic regression algorithms in R using the Tidy Models package. Specifically, throughout, we're going to be modeling whether or not it rains tomorrow by today's humidity level and sunshine. For this analysis, we'll need the Tidy Models and Tidyverse packages, as well as some data from the Rattle package. Checking out just the first few rows of the data for each day of or sample of days in Sydney, Australia, we have information about whether or not it rained the next day, yes or no, as well as the current day's humidity level and sunshine. Now, in building the logistic regression model of rain tomorrow, what we want to do in particular is model the log odds that it rains tomorrow. That is, we want to model the yes category of rain tomorrow. But R doesn't know this, so we have to explicitly tell R that this is the case. Another way to think about wanting to model the yes category is that we want to treat the no category as the reference level of rain tomorrow, kind of the level that we don't care about. So in order to specify this in R, we're going to mutate our rain tomorrow variable to a re-leveled version of the original rain tomorrow variable. So we're going to re-level this variable using no as our reference category. So mutate helps us basically replace the existing or original rain tomorrow column with this new re-leveled version, and we're going to store it back in our Sydney dataset. So that's step 0, just to make sure that we're modeling what we think we're modeling here. And then the next steps are the same as usual. So in step 1 of building our logistic regression model, we need to specify that this is the algorithm that we plan to use. So to begin, in our logistic spec or specification, one new thing that we'll be using here is logistic reg. So we're not doing a linear regression, we're doing a logistic regression. Further, we're now working in a classification mode or setting where our y outcome variable, here rain tomorrow, is categorical. So we're doing a classification task. And the function or engine within R that we'll use to build our logistic regression models is called GLM. That stands for Generalized Linear Models. So all we're doing is setting up the structure of the algorithm that we plan to use. We're not giving it any data or variables, and so we're not yet fitting the model. We're just saying what type of model we eventually are going to want to build. All right, so in our second step, now that we've built our model, we can specify our variable recipe. Now in logistic regression, we do not have to do any pre-processing steps. Mainly, we do not have to standardize or normalize quantitative predictors, and we do need to use dummy variables for our categorical predictors, but this is done automatically in the background by the GLM function. So in most cases, our variable recipe will be very simple. Using the recipe function, we just need to specify the variables in our analysis and where to find them. So here we want to model rain tomorrow by our two predictors, humidity 9 a.m. and sunshine. And we can find these variables or ingredients in our Sydney dataset. So again, in this step, we're just indicating the ingredients of our model, but not the type of model that we want to build. So in step 3, our workflow is where we combine the information about our model or algorithm, as well as the information about our variables in the variable recipe. So to build this logistic workflow, we use the workflow function. And to this workflow, we add our variable recipe. Whoops. And we add our model. And above, we stored our variable recipe as variable recipe, not very creative. And we stored our model as logistic spec. So now we have our workflow, but this workflow hasn't yet built any model. It's just specified basically the pieces of information that we are going to eventually use to build this model. So it's in step 4 that we actually build it. That is, that we actually estimate the logistic regression model. Now in logistic regression, there are no tuning parameters here, and so we don't have to build it for a range of tuning parameters. We just need to fit the model one time. That is, we do not need to tune the model for a grid of various tuning parameters because there are no tuning parameters. So in step 4, to build our logistic model, we need to take our logistic workflow that we just defined above, and we're going to use that workflow to fit our relationship using the Sydney data. All right, so now we have our logistic model and we can inspect the results and apply them. So the next thing that I want to think about is the model coefficient. So basically just exploring the general properties of our model. So here for our logistic model, as usual, when we want to get a kind of a basic summary or specifically a table of coefficients, we can use the tidy function. This is just like in least squares and lasso. So here we have a table of coefficients, but remember that by default, our logistic regression models are on the log odds scale. That is, we're modeling the log odds of rain tomorrow. And so the coefficient estimates are on that log odds scale. Also recall that we can transform these coefficients to the odds scale by exponentiating. And so we'll do that next. So we're going to take this tidy table, the same tidy table that we saw above, and we want to tack on some new columns that transform the coefficients. So to tack on columns, we can use the mutate function. When we transform our coefficients to the odds scale, recall that we can interpret them as odds ratios. So I'm going to label the new coefficients on the odds scale as OR for odds ratio. And I obtain these by exponentiating the original coefficients, which, recall, were stored under the estimate column. So I can exponentiate the estimate column. I also want to get information about the errors on the odds scale instead of errors on the log odds scale. But instead of just transforming the standard errors, I'm going to use the errors in combination with the estimates on the odds scale to get a confidence interval for the coefficients. It's a little bit easier to interpret. So to get the lower end of the confidence interval for our odds coefficients, we can exponentiate the estimate minus roughly 2 times the standard error column. And how is that labeled here? STD point error. Okay. So I'm taking my estimates and subtracting roughly 2 standard errors, but then exponentiating it. Similarly, to get the upper bound of my confidence interval for the odds scale coefficients, I can take the estimate plus roughly 2 standard errors. Right, so again, the idea here of our confidence interval is that on the log odds scale, we're going to take our estimate plus or minus 2 standard errors, roughly. 1.96 is just a little bit more precise. But then to get them on the odds scale, we'll exponentiate. So if we run that code, and we look at the last 3 columns, those are the columns we defined. So they give us the information about the standard errors on the odds ratio scales, as well as not just our best guess of the coefficients, but essentially a range of possible coefficients as expressed by the confidence intervals here. So these confidence intervals, again, just give us a sense of the error in our coefficient estimates and incorporating that error, what's a range of values for the coefficients. Okay, so that's the coefficients. Frequently what we're going to be doing with classification models, per the name, is using them to make classifications. So for example, suppose that today has a humidity level of 90% and there are 2 hours of sunshine. And I want to use our logistic model to predict or calculate the probability of rain tomorrow and in turn make a classification. So to make a prediction, I need to take my model, because I'm going to use the information in that model to make the predictions. And then to make the predictions, I can use the augment function. So I'm going to augment the information in my model for the new data. Here, the new data is just that example day that we defined above. So here we have, again, the information that we plugged in. Our day has 2 hours of sunshine, 90% humidity, and plugging these into our logistic model, we get out that the probability of rain tomorrow is 66.9%, which means there's a 33.1% that it does not rain tomorrow. And since this probability of rain is bigger than the probability of rain, by default, we'll classify this day as yes. That is, we'll predict that yes, it will rain tomorrow. Now that's how we get a prediction for just one day. Say if I wanted to use my model to predict rain in the future. But we can also use some of these tools to evaluate the classifications from this model. So instead of trying to make a prediction for the future, we can get probability predictions and classifications for each day in our observed data set. So we'll store these predictions as our in-sample classifications. In-sample because right now we're going to use our logistic regression model to make classifications and predictions just for the days in the same sample data that we used to build the model. So again, we're going to get those by taking the logistic regression model, augmenting it with new data. That new data here is the entire Sydney data set. So it's just the same code as above, except instead of plugging in one potential data point, we're plugging in all of our data points in our sample and storing them as in-sample classifications. And so if we look at the first 6 outcomes here, we have our first 6 data points, and for these first 6 data points, what was the probability of rain, the probability of no rain, and the corresponding classification, yes or no. Okay, so what we really want to do is be able to compare the observed rain outcomes with these predictions. So just for the 6 first data points here, we see that the first 5 classifications were correct. They all predict yes, rain, and in fact, it did rain. But the 6th classification was incorrect, right? Our model predicted that it would not rain, but that it did. So we want to do point-by-point or day-by-day comparison of the observed rain to the predicted rain for each day in the data set. So to get this information, we can use an in-sample confusion matrix. So what we want to do is take our in-sample classifications, so the information in this exact table here, and break it down using a confusion matrix. To get a confusion matrix that tells us about the correct and misclassifications, we can use the confmat function, and it requires 2 pieces of information. In our in-sample classifications table, which column indicated the truth and which column indicated our model estimate or our classification. In our in-sample classifications table above, the truth was stored as rain tomorrow. That's what actually happened. And our model prediction or estimate of what would happen was stored as .pred underscore class. So .pred underscore class. So again, we're taking all of those classifications and building a confusion matrix. And we can check that out in various forms. First, in table form, we can just print out what we stored in sample confusion. All right, so this breaks down what actually happened. Did it rain? Yes or no? And what did our model predict? Yes or no? We can also check out this information of correct and misclassifications in a plot form, specifically a mosaic plot. So to get the mosaic plot, we can just take our in-sample confusion, and instead of just printing it out, we can pipe it into an auto plot. So we've seen auto plot now several times for various algorithms. It has different functionalities depending upon what we pipe into it. Here, it's going to make a mosaic plot of our confusion matrix. So let me see if I can look at this a little bit easier here. So again, it breaks down the correct classifications, the misclassifications, and that's about it. To make it a little bit easier to inspect, I'm going to add some color here. The code is a little complicated, so I definitely need to copy and paste it myself. I wasn't going to try to remember it. Let's see here. We're not going to store it. So basically, we're just taking that same mosaic plot, and we are filling the boxes, the 4 boxes in the mosaic plot, using the column names in our sample confusion table. And we need information about the number of columns in that table. So if I just show you what this piece is doing right here, I'll copy it, paste it out here. Right, it's basically just labeling these 4 boxes as no, yes, no, yes. So let's check out what happens, and then we can make more sense of why we care there. All right, so what it's doing here is it's modeling or coloring all of the no predictions as red and all of the yes predictions as blue or green here. And so now if we look in the yes truth column, that breaks down the days on which it actually rained, which we can see in size are smaller than the days on which the truth was no rain, meaning there were more days that it didn't rain than that it did. And then within any column, so the yes column, we can see that roughly half of the rain days were correctly classified as rain and roughly half were misclassified as no rain. In contrast, on the actual non-rainy days, so truth equals no, a small fraction of that whole was misclassified as rain, but the majority of non-rainy days were correctly classified as no rain. All right, so again, this mosaic plot is just a visual of the confusion matrix. Right. We also want to be able to look at the confusion matrix and get information about things like the overall accuracy of our model, the sensitivity, the specificity, and so on. To this end, we can use the summary function, and we need to pipe in the information. I already forgot how I stored it, from our in-sample confusion. So our in-sample confusion, just to remind you, was our in-sample confusion matrix. So to get the classification metrics from this table, we apply the summary function to the table, and then we have to specify event level second. This is again because R cannot read our mind, that our category of interest here and what we're modeling is the log odds of rain. So yes, rain. So event level second indicates that we're interested in this second level here. So when we apply that summary function, we get out a bunch of statistics about our classification accuracy. We'll focus on the overall accuracy of our model, which is roughly 81.3%, as well as the sensitivity and specificity of our model, which are roughly 52.6 and 91.2% respectively. All right, so 2 last things here. Above what we, the metrics that we got in our confusion matrix and the corresponding or resulting calculations of sensitivity, specificity, and overall accuracy, those were all in-sample metrics. Again, how well did our model do at classifying the same data points that we used to build the model? So just like in regression, we can get more honest cross-validation metrics. that help us better understand how well does our model classify rain or no rain on new data points. So to this end, because cross-validation is going to randomly split our data into different folds, we first need to set the seed so we get the same results every time that we run this random procedure. And then we're going to essentially build the logistic regression model of rain by humidity and sunshine 10 times using 10-fold cross-validation. So V equals 10 here. Every time that we build these cross-validation models, we're going to set aside one of the folds for testing and build the model using the other 9 folds. And we need to specify how we want to build each of those models. So logistic spec again is saying, what algorithm are we going to use? So for each training and test step in our cross-validation, we're going to use our logistic algorithm specified by logistic spec to model this relationship. And for each time through, so each time we build a training model and evaluate it on a test set, we want to calculate a few metrics. So this is where this code starts to differ from the same exact code that we used in least squares. So the only difference here, besides the algorithm that we pipe in, are the metrics that we calculate. So here we can specify that we want to calculate the overall accuracy, sensitivity, and specificity. Take some practice spelling those words. All right, so we run our model, and if we just check out what we stored here, we get a bunch of information, something about folds and metrics. If I want to get just the final cross-validated estimates of our 3 metrics, we can do just what we did for least squares and calculate collect metrics. So this indicates that our cross-validated estimate of the overall accuracy of the model is 81.2%. Our cross-validated estimate is sensitivity is 91.1%, and our cross-validated estimate of specificity is roughly 52.7%. Now these are very, very similar to our in-sample metrics, which means that our model is performing about as well on new data points, classifying rain for new data points, as it is at classifying rain for the data points in the same sample that we used to build the model. Mainly, in short, our model is not overfit. Now these are the final metrics of the model. If we want to check out kind of where these metrics came from and to remind ourselves kind of what's happening with cross-validation, we can check out the fold by fold results by taking our logistic model CV results. And I hope this works. I think it's called unnest metrics. Maybe I'm wrong. Unnest dot metrics. There we go. So if I want to unnest dot metrics, I get the results for each fold. So when, for example, I built my model using folds 2 through 10 and I tested that training model on fold 1, I get the accuracy, sensitivity, and specificity corresponding to that step. In the second step of our cross-validation algorithm, we left out fold 2 and built the training model using the other folds. When we evaluated or tested that model on fold 2 again, we have the summary of the accuracy, sensitivity, and specificity here. So essentially, each time we leave out a different fold for testing, we get a different estimate of the overall accuracy, sensitivity, and specificity. If we want to convince ourselves that this information is what ends up being expressed in our collect metrics, for example, I can take these unnested results Maybe I just want to focus on accuracy, so I'll say filter dot metric column. I want it to only look at the accuracy outcomes. Right, so I see that each fold has a different accuracy. So I have folds 1 through 10, ignoring sensitivity and specificity here, and I want to summarize the mean estimate of the accuracy. So again, each fold giving a different estimate, and I want to calculate the average accuracy, which was roughly 81.2%, or the same number expressed in collect metrics above. And that's our logistic regression model, at least for now.